Okay, let us start our course today. So, yesterday we have discussed about wave phenomena. So, we have discussed about wave function in particular. In particular, we choose that the wave function to be sinusoidal. Okay, it's the simplest thing. Okay, if the speed or the value of the velocity v is greater than 0, then the wave moves from the left to the right. And if v less than 0, the velocity of the propagation velocity of the waves, then we get this function, and the wave moves from the right to the left. Okay, so in particular, we have that the speed of the waves is constant and depends only on the medium, not it doesn't depend on the amplitude, wavelength, or period. So this is, for example, for string waves, transversal string wave. We have mu is the mass density per length, and tau is the tension, the force at the string. Okay, we have derived that the velocity of the wave, the propagation velocity of the waves is square root over tau, square root of tau over mu. Okay, so this is the derivation. Yeah. Okay, I replace that tau by f in this case. Okay. We just consider this line element infinitesimal. Okay. So because infinitesimal, for small theta, for small angle, we have this sin theta is around theta. Okay, because theta is very small. Then using the Newton's law of motion for circular motion, we get that this equation is the net of the force at the string at the infinitesimal length. We have this 2f theta equal to r theta 2 theta. This is the mass times mu. Sorry, this is the mass, and this is the centripetal acceleration. Then we get that this f equals to mu v squared. Okay, then we have this v equal to the square root of f over mu. Okay, so v here depends only on the properties of the medium. Okay, this in this case is mu. So we see that if the tension becomes bigger, then also the speed of the waves also becomes bigger, okay? In this case. And if the density, the mass density becomes bigger, then the speed of the wave speed, then it becomes decreasing. Okay, this is as mentioned before, this depends only the nature of the medium, okay? This one. So as we know, because the wave phenomenon, it means that the phenomenon which propagates the sum of the energy, it means that the wave propagates. Equivalently, we can say that the energy also propagates. Okay. So if there is an energy, we have also a power, energy over an interval time, okay, or per time units. So this is the power. Okay, when you take this string, for example, you make a disturbance or perturbation like this, up and down. Okay, so we get, yeah, at the origin, this in this point we have this f, this is theta. Okay, this p here, p is f dot p. Okay, what we get that because f dot v, v is the velocity of the oscillation. Okay, vy, this is the y over partial, so this should be partial dou y over dou t. Okay, we get this function. Okay, because for small theta, we get that sin theta equals to theta and cos theta equals 1. Okay, because theta is very small, around 0. Okay, then we get that the power of a wave, of the wave, is Fy times Vy. Okay, from the above equation, we get that F is a constant, yeah, okay? Then you get this is the theta Vy. So we get that this Vy here is this one, okay? The speed of oscillation of the waves. Okay, we get this equation and we get this speed of the wave propagation. This is omega over k. So we get that, okay, this P equals to mu V omega squared, squared sin squared kx minus omega t. Okay, so basically, because the function is sinusoidal and it depends on t and x, yeah. Usually we talk about this average power, not the px or comma t, not general power, but we talk about average power. So the average power, we take that from certain x, yeah, and we average with respect to the t. Okay. So we get that if we take, for example, we take x equals 0, yeah. You can take x equals 0 or x become a certain point. Yeah, it's not very important, that aspect. And there is also minus omega t. Yeah, the average, this function with respect to the t is equal to this one. So this is the average power of the waves with the speed v and the amplitude squared squared. Okay. So we get that this is for example. So for string waves, okay, we get that this average value of the power, we get this one. Okay. So this is the average power. This is basically the derivative of square E, sorry, the average E over dt. Okay. So we get that this average energy per length is equal to this one. Any question so far? Hello? Any question? No? Okay. Let's continue. Okay. So we have a string with mass per length is mu 0.2 kilogram per meter. Okay. lies on slippery ground, yeah, then we get that one of the end of this, for example, on the left here, we move with amplitude 0.15. Okay. If you see that the distance between two, two hill, yeah, two hill, yeah, is 0.75. What is the average power that you give to the string? What's the energy per length from the string, and the tension of the string. What is the tension of the string? Okay. So now, yeah, question A, we get this one. Okay. We get A, mu also this 2 pi f. Okay, we have mu. Okay, this is also this is amplitude, and this is the distance between two top of the hill. Yeah. Dua perut, it means. Okay, this V coming from this lambda times F, okay? Because we have this frequency twice per second, okay? We have 2 here, 2 per second, 2 hertz, okay? We get that this velocity, the propagation velocity of the waves is 1.5 meter per second. And then we compute the average power on the string. You can insert directly to this formula, and then we get this one. Okay. In the energy per length, we get this one. You just insert the result before, then we get this one. Any question? Any question? Hello? Hello, hello? Okay. So this is the power, okay. So what about the tension of the string? So we have this formula, this expression, okay, this F equal mu V squared. We get that mu is 0.2, and the velocity of the propagation velocity of the waves is 1.5. Okay. So we get that the tension on the string we have 0.45 Newton. Okay. This is, for example, in the case we have waves, yeah, a wave. So if the amplitude and the wavelength becomes twice, okay, how many change that the average power carries by the waves, okay? The propagation speed is not changed, okay, whether this is 1, 2, or 4. Let me ask. Keana, halo? Keane. Hello, Keane.
Yes, Pak. Sorry. Yeah.
Okay. What is your answer? 1, 2, or 4?
I think it's 2.
2. Okay. Humam Putu?
Yeah, Pak. I think it's 1, I think.
1. Okay. Reno? Reno, hello, Reno. Something wrong with Reno? Muhammad Faza. Muhammad Faza.
Hello, sir. Yeah,
Yes.
I think it's 2 as well, sir.
Sorry?
I think it's 2 as well.
Okay. Let's see ya.
Pak,
Yeah.
is it for the amplitude di kuadratin gitu?
Okay. Let us discuss. So this is the average power. This one, okay. So the comparison between PF and PI, okay, because we have the same mass density and this velocity, okay, we can divide it by itself, okay, becomes 1, and we left with this expression, okay, omega squared, omega f squared times f squared over omega I squared times I squared. Okay, what is the question if we take the amplitude and the wavelength becomes twice? Becomes 2 times, okay? Amplitude and the wavelength. So if we use this expression, we will get this expression, okay? Because lambda final, it is 2 times or than lambda I, is the half mRF. The final amplitude of this I is twice than more than 2 times more than this I, okay? So we get this is a quarter and this is 4, okay? And this we end up with this with 1, okay? So it means that if we change the amplitude and the wavelength become twice, we get that they have the same average power. Okay? Is that clear, or you have any question in mind? Any question? Hello? Clear, yeah? Okay. Let us continue. So, superposition. Okay. What happens if we have more than 2 waves? At least 2 waves, for example. We will have superposition of 2 waves. Superposition means it's the summation of 2 waves. Because this happens and this is possible because the waves equation is a linear equation. So we can say that if we have C1 and C2, for example, it's the solution of wave equation, then the summation of C1 and C2 is also the solution. Okay, so this, for example, we have two waves. Okay, they have the same phase but different direction. on the left is left to the right, on the right, right to the left, okay? And this one, yeah, they have different phase, okay? The difference is pi, okay? Because the other one is, this is minus and this is plus, okay? So, for example, we have on the right-hand side, we have the figure that we have this waves with amplitude A, which is bigger than this second wave, okay? If these two waves coincide, okay, so somehow the amplitude is the summation of these two waves, okay? And then after that, they will spread again, yeah? And this again also spread. And this is the simulation, yeah, of two waves, yeah, for example. So this is this example. The waves is two Gaussian wave pulse, yeah, traveling on a string. Okay, the left hand side moving from left to the right, and the right moving from right to the left. Okay, and this is the sinusoidal waves. Okay. So if this one, for example, they meet maximum. Maximum meets the minimum, then it becomes 0. Okay. Somehow, if the superposition waves is 0, then okay, they have the same amplitudes, the same wavelength, the same period, but different by phase here, 180 degrees. Any question? No. Okay. Okay, let us continue. So the superposition principle. Okay. If waves that overlapping can be summed to get the new waves, okay, as a resultant waves. So this is the formulation. We have y1, yeah, y1 and y2, okay. This is the solution of the waves equation, both of them, and the summation of this y we result the resultant waves here. Okay. So these overlapping waves doesn't change the direction of the propagation of each wave. It's similar. Why is the superposition works? Because as I said before, these waves, yeah, y1 and y2, they satisfy the same wave equation. Okay. Then we get this new solution of wave equation. This is the analog with the oscillation, harmonic oscillation, as you discussed last semester. So we get also have a phasor summation. Okay. So phasor basically is a vector with amplitudes Ym of the wave, and it rotates with respect to this initial point, yeah, with angular speed omega of the waves. Okay. So this is for this is for simplicity. The phasor, we could use this summation of the phasor if the waves which will be superpositioned have the same angular speed. Okay, and but they can also have different amplitude. Okay, this, for example. So we have E0. E0 is the amplitudes of the waves. Okay, this E1 is a projection of phasor A0 to the vertical axis. Okay. Okay. So this we have two waves, okay? E1 and E2. This ER is the maximum amplitudes of the resultant waves, okay? EP, okay? So this phi here, phi is the phase difference. So we will write the resultant wave should be EP equals ER times sinus omega t plus alpha. And this is, for example, for many waves. Yeah? For many waves, but they have the same amplitudes. They could be also superposition. Okay, let us continue. Is there any question? No. Before I proceed. Okay, let us continue. Interference. Okay. Basically, interference is the superposition of two waves or more, yeah? With the same amplitude, the same, it could also different wavelength, but they have the same the same speed, but different in phase. This, for example. Okay, so this is the example. This Y1 is equal to this one, and this Y2 is this one. Okay, the difference is the phase. So what happens if we superposition, we sum these two waves? Okay, we get from the sinusoidal properties of the function, the sinusoidal function, the properties of sinusoidal function, we get that the summation of two sinusoidal waves, we get this one. Okay, this is only using this trigonometric identity, trigonometric properties. Okay. So you see that this is the amplitude, okay? The amplitude is Ym cos phi over 2, okay? So the interference will be constructive. It means that if this is the light, becomes brighter, or if this is sound, it becomes louder, okay? So for constructive interference, we get that phi is 2 pi times m, okay, where m could be 0, 1, 2, or plus minus. But destructive, it means that this phi is equal to m plus half, okay, times 2 pi, where m goes from 0, 1, 2, and etc. and so on. So constructive means we have maximum amplitude. And this is, let's say, this minimum amplitude. This is brighter and this is darker. This is louder and this is silencer. Okay, so this is the problem. So consider two identical waves. They have, they move parallel, and they have the phase difference is pi over 2 radian. What is the amplitude of the resulting wave expressed in the amplitude Ym from each wave? Okay. So, for example, we have Y1 and Y2 like this, okay? So they move in the same direction to the left and to the right, to the left and to the right, okay? But they have different phase, okay? So we will get from the sinusoidal properties, we will get this function, okay? Then we get this, the amplitude A is equals to 2Ym cos phi over 2, okay? Okay. Okay. So, what does it mean, this constructive and destructive? So, this is, for example, constructive, yeah, because they have the same phase, but this is destructive because they have pi, the phase difference is phi. Okay. Sorry. Okay, so this is, for example, the amplitude. They have the same amplitude, but the angular momentum is omega 2 is 1.15 omega 1. Okay, they have different angular speed, angular velocity. Sorry, angular frequency. So we will get that if A plus B, and then we get this one. So you see that this the minimum of this picture represent this destructive interference. While if we have the maximum value of the speed, we will get this constructive interference. Okay, this maximum indicator. So, because we have two angular velocity, we will get from this superposition, we will get this omega L is the low frequency, which is omega 1, sorry, omega 1 minus omega 2, and this is omega H is the higher frequency. Yeah? This is omega 1 plus omega 2. Okay, and you see that at this around this 0, we get the lowest angular momentum. Okay, and this one have maximum angular momentum. Sorry, angular frequency. Any question? So this is the simulation. Okay. . Any question? No. Okay. So one of the properties of the waves, it can be reflected. So somehow, for example, we have this pulse, for example, wave pulse, yeah, from right to the left, okay, and we at the end we get a fixed end, okay, this fixed end, and this fixed end, they will have the reflected waves will have different phase, yeah. For example, the different phase is 0, and the different phase of the reflected waves is pi, okay, 180 degrees. Okay. What about if the end is free? We call it this free end. Okay. If the wave reach this end, the reflected waves will have the same phase as the incoming waves. Okay. This V here is still the same, okay? Only the function of the waves. This is the simulation. So this is the fixed end, and this is the free end. Okay? So reflection of the waves. Reflection of the waves. Sorry, this is, we call it, I forgot in English. I forgot. Do you know the English words for pelayangan? I forgot this the notion. Okay. Let's see what the Resnick book said about it.